Joining us now is Dr. Nikki Fox. Dr. Fox, three missions are launching this week. Can you kind of give me a run through what those missions are and kind of the purpose of each one?
Absolutely. We're really excited. All three missions actually launching on one rocket, which is a credible way to get a lot of science into space for less money. So we're really excited about that. IMAP, the sort of main mission on that stack, is going to be studying what is coming from the sun. So basically, sitting and sensing everything that comes in the sun's atmosphere towards the Earth. Really excited about the fact that we'll be doing forecasting and really helping to protect our astronauts on Artemis 2 and Artemis 3 with this IMAP data. IMAP also looks at the boundary to interstellar space. And so this atmosphere from the sun bathes all of the planets, carves out a protective area for our solar system, protects us from the vagaries of interstellar space, very high radiation that can come in through galactic cosmic rays. So basically doing, all of those pieces. The Carruthers Geocorona Observatory, also launching on the stack, will look at kind of the final boundary between the Earth's atmosphere and deep space. We call it the exosphere. And that mission will be looking at kind of how this region of our atmosphere, it's never really been studied before, and how that, kind of responds to what is coming from the sun. So IMAP and Carruthers making a really close partnership. And then we're really honored to be launching the NOAA Space Weather Follow-on L1 mission, otherwise known as SWIFO, that will be providing operational space weather data for the nation.
Let's talk about the solar atmosphere for a second. I was reading up on it, and it does kind of abruptly stop at a thing called the terminus shock. So, what do we know about this terminus shock, and what are we trying to learn with IMAP about how kind of the boundaries of this atmosphere?
So that's a really great question. We had a sort of precursor mission to IMAP called IBEX, the Interstellar Boundary Explorer. And that's how we know that the technique that we're flying on IMAP works to actually map this boundary. It's through a process called energetic neutral atom imaging. So, basically all the neutrals that are out all the ions that are out in the very sort of far region, they can grab an electron, it becomes a neutral atom, it gets a lot of energy, and it streams in towards the sun. And so it will hit the detectors on IMAP, and that allows us to gradually build up maps of what this boundary actually looks like. The termination shock we know a little bit about because our two amazing Voyager spacecraft have actually crossed both the termination shock and the actual boundary itself, and they are out in interstellar space. Voyager 1 kind of went out to the north, and Voyager 2 down to the south. So we've had, we know what the boundary kind of looks like in terms of the data from Voyager. And then IMAP is going to take much, much higher resolution, sort of mapping and images of that boundary itself, building on the first measurements from IBEX and now adding much higher resolution. And it's in going to the L1 point means there's no obstruction. The Earth is never in the way, and it can really stare at the interstellar boundary all the time. It takes 6 months as the Earth goes around the sun, the L1 point goes with it. And so every 6 months, IMAP will be able to basically stare at the entire sky and then map out what this boundary looks like.
Why do we care about this boundary? Why is it important to understand how the sun and its winds work within our solar system?
So for us to understand, to be able to predict space weather, to protect our astronauts, to protect our technology here on Earth, we really need to fully understand exactly how the sun's atmosphere works, how it interacts with our Earth's protective magnetic field, and how that energy comes in and sort of changes. It causes the atmosphere to glow. That's what you see when you see an aurora. And it affects a lot of our technology here on Earth. But that boundary, that very far boundary, protects us by orders of magnitude against these galactic cosmic rays. That's really important for us to understand this boundary, because as we, obviously we're sending astronauts to the moon, but then we have our eyes on Mars after that. And that is putting astronauts on long duration trips through interplanetary space between Earth and Mars. And so really understanding how these cosmic rays are, how they're shielded, what they look like, how they're going to impact that crew vehicle is very important.
With Corelliers looking at this other atmospheric, barrier, what's the difference between the solar winds, the barrier they're hitting versus the Earth winds hitting the solar winds? What's the difference between those two barriers?
Oh, that's really interesting. So the exosphere is kind of the final boundary before you hit outer space. So even though it is still, it's still the Earth's atmosphere, it's very, very, very tenuous at that point. So terrestrial weather isn't playing a big part. At that point, you're really just looking at how space weather is hitting that sort of big boundary. So the magnetosphere, the magnetic bubble that our planet kind of protects us with, that's sort of where we're getting to the edge of that region, and we're able to look at sort of how the energy will enter in and cause us to get kind of the atmosphere gets excited and lots of electric currents flow, and that's what we want to measure. The boundary where sort of terrestrial and space weather interact, that is down lower. That's in the sort of ionosphere thermosphere region. So we've done some really great work looking at that boundary with early missions in the heliophysics fleet like ICON that sort of actually really studied that boundary. We have a mission called GOLD that is sort of taking images of that region and looking at how that's changing. And then we have a mission on the International Space Station called OR that looks at gravity waves that are flowing through that region. So we have missions that look at kind of all of the different pieces of the space weather puzzle, but we've never had a mission that looked at the edge of the exosphere or the geocorona. The best measurements we have of that actually are from a camera that flew with Apollo 16, and the astronauts took that down to the lunar surface, and they were able to image the geocorona. So basically how this area kind of lights up because of light from the sun, because of the interaction with the photons. The camera, incidentally, is still on the moon, but the astronauts brought back the very precious film canister, and there are images from that camera. The camera was designed by George Carruthers, and so that is why the mission is named, because of this iconic image that was taken by the Apollo 16 crew. So this is, another piece of the puzzle, another piece of how our planet is responding to what's coming from the sun.
How has technology shifted? We took photos since on the moon. How has the technology shifted? What sort of tech are we working with now to further analyze this atmosphere?
Yeah, we're working with very, very sophisticated imagery now. So being able to look at the geocorona and how that is sort of illuminated by the sun's light. We're able to do that with a couple of different cameras. We've got like a wide field imager that will, look at the whole thing. We've got a more narrow one that looks in more detail at the different wavelengths and how everything is sort of acting together to perform that protection duty that we rely on here on Earth. But really, it's just, if you think about the technology that would have existed during the Apollo era, like think about a telephone that would be on the wall, a rotary dial telephone, and now look at the technology you hold in your hand with a smartphone. And that's the sort of the leaps that have happened in technology, a lot of it driven by the NASA program, and the need to always fly better technology, to be able to do bigger and better and bolder missions and answer bigger and bigger science questions. And so the technology that we develop at NASA, often you'll find that you are things you didn't even know you needed many years ago that we now rely on all the time.
There's a third mission on this launch. I don't want to ignore it. So kind of touch on that mission a little bit. What is that mission and why is it important for us on Earth?
Yeah, we're very proud to be launching our NOAA Space Weather Follow-on L1 mission. That also going up on the ring. So Carruthers on one side and SWIFO on the other. SWIFO is going to be also hanging out at the L1 point. and it will provide a critical real-time space weather data, which our NOAA forecasters will use for the space weather forecasting for the nation. So a really, really important mission. So, I kind of think about it as the sort of ultimate like space weather gang out there at the L1 point. IMAP doing precision measurements of everything coming from the sun and then telling us about that very, very far away boundary. Carruthers telling us about how our sort of planet's atmosphere is responding to space weather, and then SWIFO providing that real-time operational space weather. So it's just a really cool stack of missions going up.
Space weather itself, why do people on Earth need to care about it? It's pretty cool, but why do they need to care about it?
So we literally rely on technology that can be impacted by space weather. So things like your GPS signals that we all rely on to get from place A to B. We also have farmers that rely on it to do precision agriculture, drilling, mining, all of the things that require really, really precision. They can be impacted by changes in the magnetic field configuration and by electric currents flowing. And so, there's a lot of economic benefit to being able to actually predict. If you know a big space weather storm is coming, you can protect a power grid so you don't get, like a transformer that fails and a whole power grid goes down. You can actually protect against these things by knowing that they're coming. So a lot of really things that you wouldn't think about actually are susceptible to space weather.
Fantastic. Dr. Nikki Fox, thank you so much for chatting with us today.
Thank you so much.